It's your boy, BeaconBot. We're back again. Time for a little, it's kind of nightly now, but nightly AI deep dive. Trying to do one every day. Sometimes we're reading paper, sometimes we're looking at code, sometimes I've got random rants, sometimes we're reading tweets. I don't know what's going to happen every night. Something new happens every single day. Today, we've got a new little paper that looks like it was dropped by Google. It's on Kaggle. It's a very low quality uploaded onto Kaggle for some reason, but we're going to take a little read through AI agents. It's also the 1st February. We did every single day of January. We just messed up our audio once, so first day of February, and that also means dry January is over. It's Saturday night. That means I can drink a beer while I do this, so it's going to be fun. Got the Donkey Kong 2 Forest Interlude 1 hour going. It's a good song for reading things too. Let's dive right in. Humans are fantastic at messy pattern recognition tasks. However, they often rely on tools like books, Google search, or a calculator. To supplement their prior knowledge before arriving at a conclusion, just like humans, generative AI models can be trained to use tools to access real-time information or suggest a real-time action. For example, a model can leverage a database retrieval tool to access specific information like a customer's purchase history so it can generate tailored shopping recommendations. Alternatively, based on a user's query, a model can make various API calls to send an email response to a colleague or complete a financial transaction on your behalf. To do so, the model must not only have access to a set of external tools, it needs the ability to plan and execute any task in a self-directed fashion. This combination of reasoning, logic, and access to external information that are all connected to generative AI models invokes the concept of an agent, or a program that extends beyond the capabilities of a generative AI model. This white paper dives into all of these and associated aspects in more detail. Okay, we got Julia, we got Patrick, we got Vladimir, Google, reviewers, contributors, technical writers, designers, September 2024. This came out earlier. I just didn't read it. Why didn't I read it then? I don't know. We'll be caught up one of these days. Okay, this combination of reasoning and logic and access to external information that are all connected to generative AI. I just read that. Why would you... What? Do you expect us to read the paper? Why would you put a big... Okay. Introduction. Wait. Okay, I just read that and somehow I got lost. Sorry. I'm very stupid. What is an agent? In its most fundamental form, a generative AI agent could be defined as an application that attempts to achieve a goal by observing the world and acting upon it, using its tools that it has at its disposal. Agents are autonomous, can act independently of human intervention, especially when provided with proper goals or objectives they are meant to achieve. We know what agents are. Agents could also be proactive in their approach to reaching their goals. Yes, that's the key, proactive. Who wants a reactive agent? That sounds like a bot to me. Agents when you become proactive. Bots, that's reactive. Even in the absence of explicit instruction sets from a human, an agent can reason about what it should do next to achieve its ultimate goal. While the notions of agents in AI is quite general and powerful, this white paper focuses on specific types of agents that generative AI models are capable of building at the time of publication. In order to understand the inner working of agents, let's first introduce the foundational components that drive the agent's behaviors, actions, and decision-making. The combination of these components can be described as cognitive architecture, and there are many such architectures that can be achieved by mixing and matching these components. Focusing at the core functionalities, there are 3 essential components in an agent's cognitive architecture shown in Figure 1. So we have, right here, they are saying the entire agent runtime consists of tools, a model, orchestration. Model being the fundamental model, whether that be something like a ChatGPT o3 Mini High, or a DeepSeek, or a Claude. It also could be, an image model, a Stable Diffusion, or a DALL-E. The orchestration, that's a combination of memory. Memory could be a vector database of some sort. Model planning, based reasoning, planning, profile goals, instructions. Okay, something that's keeping track of where you're progressing through a goal. And then there's tools. What could those tools be? I don't know, a bunch of different stuff. Could be APIs and stuff. So, in the scope of the agent, a model refers to an LM, a language model, not even an LLM, that will be utilized as the centralized decision maker for the agent process. The model used by an agent can be one of multiple LMs of any size, large or small, that is capable of following instruction-based reasoning and logic frameworks, like React, Chain of Thought, Tree of Thoughts. Models can be general purpose or multimodal or fine-tuned based on your needs of your specific agent architecture. For best production results, you should leverage a model that best fits your desired end application, and ideally that has been trained on data signatures associated with a tool that you plan to use in the cognitive architecture. It's important to note that a model is typically not trained with specific configuration settings, tool choices, orchestration, reasoning of an agent. However, it's possible to further refine the model for an agent's task by providing examples that showcase the agent's capabilities, including instances of the agent using specific tools or reasoning. Okay, we got it. The tools. Foundational models, despite their impressive text and image generation, remain constrained by their inability to interact with the outside world. Tools bridge this gap, empowering agents to interact with external data and services while unlocking a wider range of actions beyond that of the underlying model alone. Tools can take a variety of forms and have varying depths of complexity, but typically align with the common web APIs like get, post, patch, delete. For example, a tool could update customer information in a database or fetch weather data to influence a travel recommendation that the agent is providing the user. With tools, agents can access and process real-world retrieval. This empowers them to support more specialized systems like RAG, which specifically extends an agent's capabilities beyond what the foundational model can achieve on its own. We'll discuss tools in more detail below. But the most important thing to understand is that tools bridge the gap between the agent's internal capabilities and the external world, unlocking a broader range of capabilities. Okay, it all makes perfect sense. We understand all of it. We're very smart. Let's try a little medieval soundtrack. The orchestration layer. Oh, that's lovely music. The orchestration layer describes a cyclical process that governs how the agent takes in information, performs some internal reasoning, and uses that information to inform its next action or decision. In general, this loop will continue until an agent has reached its goal or stopping point. The complexity of an orchestration layer can vary greatly depending on the agent and task it's performing. Some loops can be simple calculations with decision rules, while others may contain chain logic involving additional machine learning algorithms or implement other probabilistic reasoning techniques. We'll discuss more about the detailed implementation of the agent orchestration layers in the cognitive architecture section. Lovely. Agents versus models. Got a little chart here. To gain a clear understanding between the difference between an agent and a model, consider the following chart. A model. Knowledge is limited to what is available in the training data. An agent could be extended through the use of tools. What are tools? Tools are things that bridge the gap between an agent's internal knowledge and the knowledge of the outside world. That could be gathering knowledge through something like an API, maybe gathering knowledge through something like a vector database using a process like RAG, Retrieval Augmented Generation. That's what makes it not just a model, but an agent. Models. Single inference prediction based on user query. Unless explicitly implemented for this model, there is no management of session history or continuous context, i.e. chat history. Now, agents manage chat history, i.e. manage session history, i.e. chat history, to allow multi-turn inference prediction based on user queries and decisions made in orchestration layer. In this context, a turn is defined as an interaction between the interacting system and the agent, i.e. one incoming event, one agent response. Models, no native tool implementations. Agents, tools are natively implemented in an agent architecture. Models, no native logic layer implemented. Users can form prompts as simple questions or use reasoning frameworks like chain of thought, React, etc. to form complex prompts to guide the model in prediction. But agents have native cognitive architecture that uses reasoning frameworks like COT, React, and other pre-built agent frameworks like LangChain. Cognitive architectures, how agents operate. Imagine a chef in a busy kitchen. Their goal is to create delicious dishes for restaurant patrons, which involves some cycle of planning, execution, and adjustment. They gather information like a patron's order and what ingredients are in the pantry or refrigerator. They perform some internal reasoning about which dishes and flavor profiles they can create based on the information they have gathered. They then take an action to create the dish, chopping vegetables, blending spices, searing meat. My meat. As at each stage in the process, the chef makes adjustments as needed, refining their plan as ingredients are depleted or customer feedback is received, and uses the set of previous outcomes to determine the next plan of action. The cycle of information intake, planning, execution, and adjusting describes a unique cognitive architecture the chef employs to reach their goals. Oh my god, it's almost like we're agents. Wow. It's almost like the agents are modeled after how humans work. Wow. Just like the chef, agents can use cognitive architectures to reach their end goals by iteratively processing information, making informed decisions, refining their actions based on previous outputs. At the core of agent cognitive architectures lies the orchestration layer, responsible for maintaining memory, state, reasoning, and planning. It uses the rapidly evolving field of prompt engineering and associated frameworks to guide reasoning and planning, enabling the agent to interact more effectively with its environment and complete tasks. Research in the area of prompt engineering frameworks and task planning for language models is rapidly evolving, yielding a variety of promising approaches. While not an exhaustive list, here's some of the popular frameworks and reasoning techniques available at time of this publication. And things are changing all the time. That's why we're here every day, reading, learning, doing something. React, a prompt engineering framework that provides a thought process strategy for language models to reason and take action on a user query, with or without in-context examples. React prompting is shown to outperform several SOTA baselines and improve human interoperability and trustworthiness of LLMs. There's also your chain of thought. prompt engineering framework that enables reasoning capabilities through intermediate steps. There are various sub-techniques of COT, including self-consistency, active prompt, and multimodal COT, that have strengths and weaknesses depending on the specific application. Finally, we have TOT, Tree of Thoughts, a prompt engineering framework that is well suited for the exploration or strategic look-ahead task. It generalizes over chain of thought prompting and allows the model to explore various thought chains that serve as intermediate steps for general problem solving with language models. Cool. Lovely. Ooh, I like this. I like this middle of the music. It's nice. Agents can utilize one of the above reasoning techniques or many other techniques to choose the best action for the given user request. For example, let's consider an agent that is programmed to use the React framework to choose the correct actions and tools for the user query. The sequence of events might look like this. User sends query to the agent. Agent begins the React sequence. The agent provides a prompt to the model, asking it to generate one of the next React steps in its corresponding output. Whoa. Okay, I'm going to turn this down a little bit. It got a little intense. Okay, question. The inputs question from the user query provided by the prompt. Thought, the model's thought about what it should do next. Action, the model's decision on what action it should take. Action this is where tool choice can occur. For example, an action could be one of the flight search code none, where the first three represent a known tool the model can choose, and the last represents no tool. Action input, the model's decision on what inputs to provide the tool, if any. Observation, the result of the action input sequence. The thought, action input, observation, and repeated n times as needed. And then final answer, the model's final answer to provide the original user query. The React loop concludes and a final answer provided back to the user. Okay, cool. Whoa, calc, that's short for calculator. Cool, nice. Okay, as shown in Figure 2, the model tools and agent configuration work together to provide a grounded, concise response back to the user based on the user's original query. While the model could have guessed at an answer hallucinated based on its prior knowledge, instead use a tool of flights to search for real-time external information. This additional information is provided to the model, allowing it to make a more informed decision based on real factual data and summarize it back to the user. Okay. In summary, the quality of agent responses can be directly tied to the model's ability to reason and act about various tasks, including the ability to select the right tools. Okay, cool, great. Next section, we'll dive into tools. Just looking how far this thing goes. Tool, wow. Tool, wow. Let's see. Tools are keys to the outside world. While language models excel at processing information, they lack the ability to directly perceive and influence the real world. This limits their usefulness in situations requiring interaction with external systems or data. This means that, in a sense, a language model is only good as what it learned from training data. But regardless of how much data we throw at a model, they still lack the fundamental ability to interact with the outside world. How can we empower them to interact with the outside world? Functions, extensions, data stores, and plugins are ways to provide critical capability to the model. While they go by many names, tools are what create the link between our foundational models and the outside world. This link to external systems and data allows our agents to perform a wider variety of tasks and do so with more accuracy and reliability. For instance, tools can enable agents to adjust smart home settings, update calendars, fetch user information from a database, or send emails based on a specific set of instructions. At the date of this publication, there are three primary tool types that Google models are able to interact with: extensions, functions, and data stores. By equipping agents with tools, we unlocked a vast potential. I know. Extensions. The easiest way to understand extensions is to think of them as bridging the gap between an API and an agent in a standardized way. Okay. Let's say you build an agent with the goal of helping you book flights. You know that you want to use the Google Flights API to retrieve the flight information. This paper was written by Google, so of course you want to use the Google Flights API. But you're not sure what you're going to get your agent to make calls to the API endpoint. One approach is to implement custom code that can take the incoming query, parse the query relevant information, make the API call. But what happens if you want to say, I want to book a flight to Zurich and never provide a departure city? The API call would fail without the required data. This approach is not scalable and can easily break in scenarios that fall outside the implemented code. A more resilient way would create an extension. An extension bridges a gap between an agent and an API by teaching an agent how to use the API endpoint using examples. Teaching the agent what parameters are needed to successfully call the API endpoint. There you go. So you could write a bunch of code and have call the APIs explicitly yourself, or you could teach the agent how to call the API and have to call the API yourself, and we've got a little bit more autonomous there. A little scarier too, but more scalable. Teaching the agent what arguments or parameters are needed, great. Extensions can be crafted independently of the agent and should be provided as part of the agent's configuration. The agent uses the model and examples at runtime to decide which extension, if any, are suitable for solving the user's query. This highlights a key strength of extensions. They're built-in example types that allow the agent to dynamically select the most appropriate extension for the task. So here we've got flight extension, map extensions, weather extensions. They all lead to different APIs. It can look through and say, okay, what are the examples? Hey, here's something that matches what I need to do right now. I need to get a flight. I'm going to go use the flight extension. Think of this as a way to solve that a software developer decides which API endpoints to use while solving or solutioning for a user's problem. Yeah, I got it. Cool. Sample extensions. To simplify the uses of extensions, Google provides some out-of-the-box extensions that can be quickly imported into your project and used with minimal configuration. For example, the Code Interpreter extension in Snippet 1 allows you to generate and run Python code from a natural language description. So we got a little Python here. We got vVertex AI. We got Pretty Print up here, project ID, region. We're knitting the Vertex AI, loading in an extension, and then we Code Interpreter. We're saying write a Python method to invert a binary tree. Okay. This is the above snippet will generate code. And then you can what is so vVertex is for running. I'm not a Python boy anymore. vVertex. This is what I should be. What is this? Vertex AI. Fully managed unified AI development platform for building and using generative AI access. It's interesting that I do AI stuff all day. All my friends do AI stuff. And I mean, no one just trusts anything that Google ever does just because, you know how they do. They make to rug every product they make. And all they do ever is announce things in papers that you can never, ever, ever use. While the other people like DeepSeek are like, yo, here's the code, here's the paper, and you can use the API now. But man, I've not been using any Vertex AI platform at all. Maybe I'll have to do an exploration of this. This will be a to-do later. Stop being a Google hater. They invented GPT. And we're disrespecting them these days because we don't use anything by them. But okay, this allows access to the Gemini models. Okay, cool. What does this do? Summarize extensions and provide a way for agents to interact, influence. Okay, well, I didn't really read what this thing does. I don't really need to care, but generate and run Python code from natural language description. Okay, whatever. This is trying to generate some Python code and actually run it to see if it actually works. Is that what we're doing here? I think so. Functions. In the world of software engineering, functions are defined as self-contained modules of code that accomplish a specific task and be reused as needed. When a software developer is writing a program, they often create many functions to do various tasks. Functions work similarly in the world of agents, but we can replace the software developer with a model. A model can take a set of known functions and decide whether to use each function and what arguments the function should take based off specification. Functions differ from extensions in a few ways. A model outputs a function and its arguments, but doesn't make a live API call. Functions are executed on client side, while extensions are executed on agent side. Interesting. Using our Google Flights example, let's look at it right here. So we've got agent, we've got function, we've got Google Flights. The difference is that the function here is that neither the function nor the agent interact directly with the Google Flights API. So how does the API call actually happen? Well, with functions, the logic and executing call of the API is offloaded away from the agent and back to the client-side application as seen in figure 8 and 9 below. This offers the developer more granular control over the flow of data in the application. There are many reasons why a developer would choose functions over extensions, but here's a few common ones. API calls need to be made at another layer of the application stack outside of the agent architecture flow. Security or authentication restrictions that prevent the agent from calling an API directly. Timing or order operation constraints that prevent the API agent from making API calls in real time. Additional data transform logic that can be applied to the API response the agent cannot perform. The developer wants to iterate on agent development without deploying additional infrastructure for the API endpoints. Function calling can act like stubbing of APIs. Okay. The difference in internal architecture between the two approaches is subtle, as seen in figure 8. The additional control and decoupled dependency on external infrastructure makes function calling an appealing option for the developer. Client-side control. So see right here, it is like right here, instead of letting the agent ever call the API directly here, you see, it ends up hitting back to whatever this front end is, and the front end is going back over here and calling this. So it's providing exactly, here's all the stuff you'd want to fill out, and then this person was saying, oh, cool, great, I want to trigger it from there, which could be good for a number of reasons, like we just described above. Maybe we have to do some sort of authentication from here to there. Maybe we want to do some transformation of this UI from here to whatever, a bunch of different stuff. Okay. Use cases. A model can be used to invoke functions in order to handle complex client-side execution flows to the end user, where the agent developer might not want the language model to manage the API execution. Let's consider the following example where an agent is being trained as a travel concierge to interact with users that want to book vacation trips. The goal is to get the agent to produce a list of cities we can use in our middleware application to download images data for the user's trip planning. A user might say, I'd like to take a ski trip with my family. I don't know where to go. In a typical prompt, the output might look like this. Here's some place you can consider a ski trip. While the above output contains the data we need, city names, the format isn't ideal for parsing. With function calling, we can teach a model to format this output in a structured style like JSON that's convenient for another system to parse. Given the same input prompt from a user, for example, the JSON output for a function might look like snippet 5 instead. Function call, name, display, city, cities, preference, skiing, okay. The JSON payload is generated by the model and then sent to our client-side server to do whatever we'd like to do in the specific case. We could call the Google Places API to take the cities provided and look up images, then provide them as formatted rich content for the user below. Okay, great. Yeah. Okay, cool. Great. Yeah, We got it. So the result of the example in level 9 is the model used to fill in the blanks parameters for a client-side UI. Yeah, that makes sense. We're filling in stuff in a client on a client that then the client can execute themselves. We're not letting it execute directly. But let's say you're trying to, fill something out. You want to do let's pretend like I wanted to build something to order things off Amazon to start a stream, right? I could have an agent that would then do a query and add a bunch of stuff to our cart, or it would populate a bunch of search results, and you would see stuff in a search query, and then you would say, what do you want to add to your cart? And once you added the cart, you could check out on your own, but it wouldn't actually do the checking out. Okay, we got some sample code in Python. Don't care. Okay, great. It's Python. It looks like English. Data stores. Imagine a language model as a vast library of books containing its training data, but unlike a library that continuously acquires new volumes, this one remains static. A model doesn't keep training on stuff, so we need data stores. How do we store data? I don't know, vector databases. Data stores allow developers to provide additional information in its original format to an agent, eliminating the need for time-consuming data transfer animations, model retraining, or fine-tuning. The data store converts the incoming document into a set of vector database embeddings so that the agent can extract information it needs to supplement its next action or response. Implementation and application. In the context of generative AI agents, data stores are often implemented as vector database that the developer wants the agent to have access at runtime. We won't cover vector databases in depth here. The key point is understanding they store data in the form of vector embeddings, a type of high-dimensional vector or mathematical representation of the data provided. Yeah, we got it. Okay, cool. I think I might. Let's see. I got it. We got how vectors work. Cool. Tools recap. We got it. Agent client side. Enhancing models with targeted learning. Retrieval and context learning, fine-tuning. Yeah, these are the different types of learning stuff. Agent quick start, trying to get you to use LangChain. That's a trick. Production application with Vertex, trying to trick you into using Vertex. That's another trick. And then we've got some endnotes. Yeah, so the last interesting thing is this. They're not tricking me into using Vertex. Come on there. They're not tricking me into using LangChain. I've already went down that rabbit hole. Is this idea of enhanced model performance with targeted learning. So there's in-context learning, there's retrieval-based in-context learning, and there's fine-tune-based learning. So fine-tune, that makes very obvious sense how that works, but that is not very flexible, and it's costly, and, well, it is flexible. I'm saying it's not flexible because you have to do it, run your model, do it, run your model. It's not growing and learning all the time. In-context learning, this method provides a generalized model with prompts, tools, and a few shot examples at inference time, which allows it to learn on the fly. The React framework is an example of this approach in natural language. Then there's retrieval-based in-context learning, and this is like doing a RAG, pretty much. And then there's fine-tune. Okay, cool. We're reading a bunch of different papers and stuff that try and break down how we divide up thinking about agents and whatnot. And we've seen different words. The concept of a room has popped up, or different types of learning in vector stores, and tools versus functions, whatever. Everyone's going to keep writing and keep defining what this language space looks like. This is definitely more of a higher level overview. Nothing super sticking out except for maybe this simple division of always between models, tools, and orchestration. It's nice, it's simple. I think it's already kind of how I was thinking, but was I calling it that? No, but okay. We'll be back tomorrow, every single day. Something about AI. If you want to review anything, just ask. Any papers, just ask. I'm a dummy. I'm learning this stuff all with you. Later. See you tomorrow.